How much of my reactant got consumed? A lot. 78%, almost 80% of my reactant got consumed. How much product did I make? 2 times as much, because it's twice as much, right? So I'm making a lot of product with very little reactant, hence my equilibrium constant is large. What do you think of that? It's pretty good, right? Let's do one more problem. Sorry? The equilibrium amount? So for this wise, for the equilibrium in your ice table, you're going to do your initial amount minus your change, that's your amount left over. So you have 1x minus 0.78x is that left over. 1 minus 0.78 is 0.22. That is the hardest part of this problem, actually. It's really difficult to see that in the exam.
I want the answer to why is it changing x?
Because I told you
Just the 78%.
I had X amount. And then I'm telling you 78.6, I got rid of the 0.6. It's supposed to be 0.786. Yeah. The answer is going to be about the same. Yeah. Yes.
So my question is, you use the ice table in this in number 5, but not in number 2.
I didn't use it in number 2.
You're looking for the pressure. So is the ice table actually
I didn't use the ice table here because I already know the equilibrium amount of one of them. I don't have to. I set up my expression. I see I have one, I know one number, I know the other. I have a single unknown. I can solve for that. You only need one equation when you have a single unknown there.
Okay, so basically, ideally, it's when we have our equilibrium, or when we don't have our equilibrium, that's when the ice table.
That's when the ice table comes in. In general, that is the case. There are some times where you have to go back to the original amount, but in that case, I give you other information as well. Okay, so just so you know. Okay, let me do one more. This one's done. Let's do 6.
Perfect.
I have a mixture of nitrogen, hydrogen, and ammonia. I have the reaction. I'm telling you I can write this equation in a different way, and then I'm telling you I can do it a different way as well. What am I trying to tell you with this type of problem? What is the purpose of this problem? What? Manipulate equations. So of course the reactions, you can have them forward, you can have them reverse, therefore I can flip them. Not only that, I can multiply them by any factors. I can multiply them by supplementing factors as well. See, this one, I didn't multiply, but I divided, correct? You should be able to manipulate K. So, equation 1 is the same thing as equation A that I showed there. See that? The only difference between equation A and the first equation is that I divided it by a half. Let me see if I can make this smaller so you can see. Yeah, there you go. Push it back there. See that? Compare these two equations. The difference is this stoichiometric factor. What is the effect that factor has on my equilibrium constant? K2 is the same thing as K1, except you're going to raise it to the power that you multiply the equation by. What is the power you multiply by? Technically, you divide it by 2, which is the same thing as multiplying by 1/2. So you raise this one to the 1/2, the original equilibrium constant.
But why?
Because I modified the second equation by that factor. You see, this is 1, this is half. The factor I multiplied the first equation to get the second was half. I know the first equilibrium constant, I can figure out the second equilibrium constant there. Correct? I actually give you a value for the first one so you can calculate that. This is the square root of the first one. Any questions about it? And then we can do the same thing for the second equation, right? The second equation, this one, is the reverse of A, correct? So you take equation A, you flip it, and you get B right here. You see that? I'm just making sure that you guys can actually see it. What do you do to the equilibrium constant if you flip the equation? The products now become your reactants, and the reactants now become your products. So that's the inverse of this, right? So you write the inverse of it. K3 is the inverse of K2, correct? Yeah.
So what are you trying, what equation are you looking at?
A and B, look at that. Look at this guy.
So you're trying to get B to
Ammonia is
A?
here. Yeah, I'm moving this, see, this one and this one are exactly the same, except the second one is this one flipped. That's what you need to recognize. Okay?
So for the answer for A, you're trying to get A to B, so for B.
No, for the answer for, it's three problems, it's two problems here. Let me make it, I don't know if you can see the whole thing. See, you're given a bunch of equations. See, the answer for A was from the first equation. It was equation 1 divided by half. Okay? Now for equation B here, it's like A. I didn't go to the first one because it's more difficult to see that. I don't know if you can see. You see what I'm doing? I'm doing a step. Because going from this one to the first one, you need to both divide and flip. And that's difficult to do in a single step. That is the inverse and then the square root of that. Correct? And as soon as they complete that. So that's why I broke it down to two pieces. So if you happen to have, this is a test taking tip. If you happen to have an equation in which you both have to flip and multiply, you know what I would do? I would break it into steps. Take my first reaction, multiply by whatever, and that's my first step, and then I would flip that one to get my final answer, just like I did in this problem. You see that? How do you go from equation 1 to equation B here? You need to divide by a half and reverse. You see? By doing that in a single step, inverse and then a square root might be too much, and your head cannot handle that, right?
If you were comparing B and 1, it would be 1 over K1 to the minus 1.
Correct. 1 over K1 squared. Yeah. So I show you a bunch of ways in which the third equation can be represented, and all of those are valid answers. For K3 being the third equation, it is yes, it is the inverse of the second one, right? So it's like that. I can express the same thing instead of with a fraction with the negative 1, which is the same thing. But I can do it with respect to the first equation as well, right?
On the exam, you're not going to give us multiple options that are correct and say which one's more correct, are you?
No, they're all correct. There's no more correctness here. These are all ways in which I can represent the answer. So I have many options for multiple choice. You see that? Yay!
So most likely we'll see which one is not likely to be an answer.
No. Well, that's actually a good exam question. But that type of question takes too long.
Okay.
Because then you have to prove that all the others are correct,
Right.
and then you find the one that doesn't work. And if I do that in an exam, the chances are you're going to make a mistake somewhere else and not get the question right, although you have the skills. So I tend to not do that in the
Okay.
exam. But it's a good exam question, though. Yeah. See, I'm glad that you can think about it already. Yes.
How do you know you always? I thought you were going to compare the third one to K1.
I did.
Oh.
I haven't.
Oh, you're just okay. You're asking.
But I'm telling you, all of these are possibilities.
Oh.
So, the sky's the limit. So the question is, can you memorize these?
No.
No way. You need to have the skill to be able to modify, flip and reverse and do all of that. Correct? It is a set of skills. This modification of equilibrium constants, MCAT problem. Yeah. Not bad, right? Perfect. Let's do more. What do we have? 7. Ooh. We have a chemical reaction. A gas becomes a gas and another gas, natural reaction. I'm telling you, I'm letting the reaction equilibrate. So now I'm at equilibrium, and at that point, I have 40% of my product, of my reactant, I'm sorry, is decomposed, right? What is the value of Kp? I want the equilibrium constant. This is similar to the first problem, except something I'm telling you here. What is the initial, what is the difference here? I'm telling you the change, correct? I know the change for my reactant is 40%. So 40% of it is going away. That's 0.4x of x. How much is left over? 1 minus 0.4, 0.6x, right? How much did I make of my product? This is 1 to 1, so therefore I made the same amount, plus 4x. And what about my other product? It's half, and therefore that is what? What is 0.4 divided by 2? 0.2, it's 0.2x. I have all my equilibrium values now in terms of x for my Kp, right? But I confused something else. I'm telling you the total pressure is 480, I'm sorry. Total pressure is equal to what? What? Adding all the partial pressures. So the sum of the partial pressures yields the total pressure. But these are all in terms of x, so I can just add them up, right? Therefore, 480 is 1.2x, correct? 0.4 plus 0.4, sorry, 0.4 plus 0.6 plus 0.2 is 1.2 x. And I solve for x. How do I do that? Divide by 1.2 both sides, right? And then I get 400x. So I know what x is. You're like, okay, that's great. I don't care about this. What do you actually want? What's the question asking you to do? Kp. So we write the expression for Kp in terms of x. So we take these equilibrium constants, we put them there. But guess what? You have x. You don't have an unknown. All you have is numbers. Plug in your number, 400, everywhere where x is, and solve.
Why did you add equilibrium?
What?
Why did you add equilibrium?
Because I have total pressures. The total pressure at equilibrium is 480. I know my total pressure is equal to the sum of my partial pressures. What do you think of that? Questions? How do I know what? How do I know it's 0.4 change? Because I'm telling you 40% dissociated. That means the 40% of it is gone. 40% means diffraction. So 0.4 of what I have at the beginning got consumed. So that is my change. That's usual terminology. So you gotta be familiar with it.
But then how do you know it's for NLBR and like why?
Oh, so I know this is for this one, but these are related to each other 1 to 1. So if I consume this much, I have to make the same amount of NO.
And then it's
And what about the other one is half, because it's, the relationship here is 1 to 1/2. Question?
So if it was like a weak acid or base, you would tell us like what percent would dissociate. But if it was like a strong acid or base, you wouldn't tell us that because it would be.
No, they react. So for strong acid and bases, this is chapter 17 and 16. This is, it goes to completion. So whenever you have a strong acid, strong base reaction, they go to completion, 100%. You do a stoichiometry problems like it's chemistry 1. Okay? And then you continue. Are we good? Questions? Can I continue? Yes?
Can you leave it in millimeters of mercury, or do you have to go to?
No, you can leave it, you can do whatever. Yeah. And we continue. Oh, this is an interesting one. Yes.
How did you get 0.6x?
How did I get 0.6 where?
1 minus 0.4.
Oh, here, 1 minus 0.4.
Oh.
Yeah. You have 1x minus 0.4x is 0.6x.
Okay, so wait a minute.
You have another one? Yeah.
So in the next one, yes, 1 minus 0.4. It says 0.4 for NO.
This guy?
Yeah.
It is the same amount because this is 1 to 1 here. only had this guy, I cannot subtract negative moles, right? If I have nothing of a product, I can only add to that product. If all I have is my reactant, I can in fact subtract from it. That's what I have a negative sign there. That is generally always the case. Correct. So I got the 0.2 because I have 0.4, but the relationship is half of it. So what is half of 0.4? 0.2. See that?
And those two should add to.
Everything else, you take these three, they're all gases. So the sum of all three gases have to add up to each other. Yes.
So the trick here is for the,
Ice table. The ice table is the trick.
and because you said sum, that means that we actually have one X.
Correct.
If I had said
So-
sum NO, then we would have to put one X over that as well too.
Which one?
For this, for the.
Oh yeah.
Right?
If you had something else, like if again you have some amount of this compound and some amount of the other one, that's X and Y. That's a different amount. Yeah, not necessarily the same. I will tell you, you have equal amounts of both, and you have X and X, and that is possible. I did that in a previous problem. Yeah. Now let's continue. Visual problem. What is happening here? I have an equilibrium. This is my reaction. 1 mole of carbon monoxide reacts with 3 moles of hydrogen gas, and it produces 1 mole of methane and 1 mole of water. Correct? I am telling you that in such this reaction, I have 3 moles of one reactant, so 3 moles, this has to be a reactant, and it is combined with 1 mole of the other reactant, and therefore this is 1 mole at the beginning, so this is the other reactant. I had no products at the beginning, so therefore C has to be a product. So that's how I know the first A and B are reactants and C is a product. That's all I know at that point. Correct?
What do you mean it has to be because of the flag flow where?
No, I know it's a product because I told you at the beginning all I have is reactant 1 with reactant 2. Because there's equilibriums in which I can actually have product at the beginning. Remember, equilibrium can begin from either side of the reaction. But I told you explicitly, there's 3 of one and 1 of the other, right? Equilibrium is reached, obviously. And I'm asking you, what is the second curve? The second curve, I'm telling you, is carbon monoxide. It's this guy. They're like, how do I know it's that particular reactant?
One third of the.
Yeah, so this one you had more. But check out, the reason I know this is hydrogen is because the slope here is quite steep. And therefore, I know it's being consumed faster than the other reactant. Which of these two is consumed faster, the carbon monoxide or the hydrogen? Hydrogen. 3 moles are consumed for every 1 of carbon monoxide. I explicitly set it up this way so that if you saw the stoichiometric ratio, you'll still get it right. But that doesn't have to be the case, because I could have done this one float slowly, and then the other one decrease faster, and then it would have been flipped. But that's a little bit more challenging to see, because then you need to know derivatives as well, so that's what I didn't do it that way.
If it were exactly like that,
It will be similar to this, yeah. I cannot take it higher than that.
you can use the stoichiometric.
You can use the stoichiometric factor if you want, yeah.
So we can't look at that graph like an X and Y coordinate. It's not going up in the X direction.
No, this is time progressing, and this is pressure of gases on this side, or amount of moles on the other side.
Okay. But you said you could flip it though, so if the top one has 3 moles.
Yeah, I can do this a little bit differently. I could have done this way, a slow slope, a big slope. See, now this would be hydrogen and this would be carbon monoxide. Because of the change, it was very slow for that one compared to that one.
Okay, so when we're finding the number of moles, we're just looking at a specific line. How big the line the job is.
See, because this is changing concentration over time, or changing moles over time, you have to see which one has the largest change, and that's I can get from the stoichiometry. Yeah.
So
But I will not do this. This is too much. I tried that once already. It didn't go well at all. Yeah, it was a bad question. It's a bad question. Yeah, they didn't like it.
So we should pay attention more to the steepness of the slope versus looking up the mole line and going, well, 1 comes before 3, the top one has to be 3 because it's higher than the.
I help you guys out. Yeah. What I was literally looking for is you guys to recognize that lines A and B are reactants and C is a product, because I didn't have any of it at the beginning. And if I can modify this question, for instance, and ask you, what happens at, what happens at this time? That's another way. At this time period in time, what happens there? At that period in time, the concentrations of all the compounds in my reaction stabilized, and therefore equilibrium was reached. That's what I would be looking for in that type of graph as well. A follow-up question is, what happens at time zero, at this time, regarding changes in concentrations? They are no longer changing, they're stable over time. That's a particular aspect of equilibrium, right? So there's a lot more information in this graph, but I think I covered much of what I will be assessing, okay?
And again, you're gonna upload all of this.
Yeah, all of it will be uploaded. Actually, I already uploaded it, I just have to publish it. Actually, I need to fix it because I have a mistake. More work. And I thought I was gonna go for dinner after this. Start my spring break. Okay, let's look at these reactions. You have 2 moles and 2 moles, or 2 moles. Wait a second. That's 2 here and 1 there. That is 3, and this is? So that's 2 minus 3 is? Oh, negative 1. And this guy is 2, and this is? So 2 minus 2 is? So the changing moles for the second one is? 0. And why do I care about this? Because Kp and Kc are the same if number of moles is the same in both sides of the equation. And this is true for the second equation only. Who likes this problem? Yay! You want to see this out, right?
Yes.
It'll probably be there at least
One.
At least one, at least one.
I can't recall. I don't know if that's the way.
If you think about it, it could be tricky though, because some people could also think of,
A solid in there, or a liquid.
yeah.
Yeah. Solids and liquids don't count.
Yeah,
Right?
that's not.
Right.
Yeah. Any questions about this particular problem?
Gross soy or
Water in the liquid phase. It has to be water in liquid. Okay? I'm gonna move quickly through this one, right? Look at this guy. They're all true. What? Let's check. A product concentration appears in the numerator in an equilibrium expression. Yes. I would hope everyone knows that. K is product of a reactant, so product is in numerator is on top, right? Good. A reaction favors the formation of the product if K is greater than 1. More product, less. This type of fraction yields a number that is greater than 1. You see that, right? More divided by less gives you a number that's greater than 1. Yes?
that's also because Q goes over K.
No, this is about equilibrium. See, because this is K. I'm talking about K, not Q. Okay? If I have a reaction favors formation of products, that means that when equilibrium is established, the product amount is greater than my reactants. That's what I'm saying with this statement. And the answer is yes, I have more product because that is the only way I can get a K that is much greater than 1.
I think you mean if this question said if Q is less than K, then it would favor the product.
If Q is less than
Then it would
K,
favor the product.
I have less
Goes to the right.
react. It goes to the right. Yeah, it progresses to make more product until equilibrium is reached. That's a different type of question, though. Yeah, that's Q versus K. That's also part of the exam, though. But it's just not this particular thing. I can put it in there, though, so you guys know how to use it. Good. Now let's talk about the last one. The stoichiometric coefficients are used as exponents in these constants. And I have a little example here, so you guys can see that that is also true.
So if you said like rate,
Oh, then the rate, I already asked that one earlier.
Oh.
The rate constant was at the beginning, and that was false, yeah. Yeah. Any other questions about this particular type of problem? Who
Wait.
likes this?
You said Q is less than K?
If Q is less than K, the reaction moves towards the right. Let's do that. Q is less than K, what does that mean? That means I have too much reactant compared to product, and to make K occur, I have to make more products, make more products, the reaction goes to the right. Correct? Good. Let's do 11. A flask contains this system at equilibrium, right? Which of these increases the solubility of copper carbonate in water? I say yes, no, and no. Let's think about the first one. Adding hydrochloric acid increases the solubility. This is a tough question because you have to recognize, oh, where is it? There you go. You have to recognize that if you have this reaction, copper goes to, copper carbonate, I forgot to put that there. Goes to copper and carbonate, right? That's my reaction, right? Hydrochloric acid is going to react with the carbonate. Why? You've seen this before. The carbonate reacts with the proton there to form, what is that called? Hydrogen carbonate, the common name. Bicarbonate. This is the bicarbonate ion, perfect. So this reacts with this to produce this. What is the effect of this reaction in the equilibrium? So I'm glad you are able to identify the reaction. Good. Now the follow-up is, how does this affect equilibrium? So two steps, right? If the carbonate is reacting with the hydrochloric acid, it is being used up. What happens to its concentration in the solution there? It will go down because it's getting used up. So this concentration goes down because it's used up in a secondary reaction. So this secondary reaction is taking it away out of the solution. What happens to my equilibrium if I remove product out of it? It shifts to the right to make more product, right? Everyone follows that? And if you're making more product, what do I have in my products? The solid or the solubility? Solubility. So if I'm making more product, then my stuff is more soluble. That's tough. Okay, I can honestly say that's a tough reaction. Yeah.
So two questions. The first one, this is copper chloride. You don't account for that. That doesn't affect equilibrium because the K value is extremely high for copper chloride. I'm saying when you add the HCl, the Cl ion doesn't have an effect on.
Oh, the chloride? No, the chloride doesn't affect because the chloride doesn't react. What is the chloride going to react with?
Well, it could react with the copper ions, but the K value would just be extremely.
No, that is too little to affect it. The chlorides tend to be soluble.
Right. So I'm saying the K value is so low that it doesn't have an effect.
Yeah, but you make very little product. You make very, very, very little product.
Right.
Yeah.
And then the second question is H2CO3. You don't account for that because again, that's an
I can make
acid.
yeah. This can go to H2CO3 as well.
But the H2, do you not account for that because it's mostly just forms the HCO3 minus?
This is a stronger base than the
Right.
HCO3, so it will react more likely with this one than with the other one.
Right,
And this is the beginning
right.
of the reaction. I'm not saying that no carbonic acid is formed. Some of it might be formed, but then it will likely decompose back to the hydrogen carbonate.
Okay.
And regardless of that side reaction, the effect is the same.
Okay, right.
It will take away this guy and make it more soluble.
Okay.
And even the chloride, if you reacted with it, then if it was making a solid precipitate, it would come out of solution and make it more soluble.
Okay.
But in this case, the chloride will have no effect.
So if you added a substance to where two soluble products were formed with both ions, then it wouldn't have an effect.
Yeah, I have an example of that.
Okay.
So for instance, I don't know if I have it. What is the other example that I have there? Sodium carbonate. No, let me write you an example of that. So let's say I have silver perchlorate, and this not perchlorate. We do silver chloride, right? And this of them and chlorides, correct?
Right.
Now, let's say I add sodium perchlorate. Does adding these salts affect this equilibrium?
No.
No. Why? Sodium reacts with chloride, correct? But that sodium chloride salt is completely soluble, and any sodium chloride that is formed, look, it will decompose back to chloride ion. So it does not consume these guys, because they still remain in solution. And what about the perchlorate? Silver perchlorate reacts as well, but that happens to be one of the few silver soluble salts, correct? And therefore it, again, doesn't consume the silver, and it goes back to solution. So addition of this to this salt, no effect on pH. But for you to be able to answer that type of question, I would have to provide you with a solubility table, because it's a little bit beyond the scope. Well, technically it's not beyond the scope, because you know solubility from Chem 1, but I don't recall how much of you remember, right? So, right? Fair enough? Yeah. So I keep it simple. Things that you do need to know: perchlorates are soluble, and what else? Nitrates are all soluble. That you need to remember. Okay?